Right, grade 12s. What I have here is I found a little worksheet resource pack from grade 12, physical science resource pack. I found it online, and it's a great content pack for just worksheets. Okay, it's not a big document. All right, it's just for term one. So it's got momentum and impulse worksheets, which we've covered, vertical projectile, and then of course the organic chemistry worksheet, which is what we want to focus on. We're not sure if we'll get to any of those questions today, of course, in the session. Rather want to start from the beginning and rather make sure we have all the content solidified. And of course, you all have been doing it, or most of you have been doing it in schools already. So you should be about 2 or 3 weeks, 2 for the minimum and 3 for the maximum, into organic chemistry already, since we only finished momentum and impulse last week by looking at a few exercises. So we won't really look at topic 2 today, but we'll rather focus on topic 4. Okay, so what we're going to start by doing here is I have a table that I'd like to construct, and it's a summary table for learning all the different groups, right, homologous groups or homologous series that exist within organic chemistry. Okay, this definitely helped me when I was in school and I was busy studying organic chemistry, as it's a great help for learning it initially, of course, and then as we go along, more practice does make perfect, because then we no longer, I won't say no longer, but we are less concerned with naming organic compounds and more concerned with reacting them in terms of let me say this, rather in terms of reacting an alkane with a with water, for example, something foolish like that, or reacting an alkane with a halogen. All right, organic substance with an element on the periodic table. Okay, so this table is going to take a while. Okay, so what I'm going to construct it first, and you can construct it with me, and or construct it when I'm done, whichever way you choose, and then we'll get started on explaining it. Okay, so we have the first part of our table according to the space that I have that I can operate in. So we construct the table into 5 different parts. So first column, the homologous series. Okay. Second, the general formula of the homologous series. Third, the functional group that obviously shows in structure, all right, structural drawing or structural formula of how that functional group would look of the homologous series, which defines obviously what it belongs to structurally. We give an example there in structural formula, and the suffix and how we can recognize which homologous series it is. Okay, so starting with the first one and the most common, alkanes. All right, alkanes, suffix ane, A-N-E. Any organic compound ending in ane, A-N-E, we know it belongs to alkanes. It has a general formula of CnH2n plus 2. Okay, what does that mean? Is that N being the amount of carbons. So for example, if we have 2 carbons, okay, we know, like as in this example, we have ethane. All right, this example will be known as ethane. Okay, T-H-A-N-E, ethane. That's that organic compound. All right, so we want to check the general formula if it's correct. Well, how many, N being the number of carbons, so Cn, so we put 2 in there, so we have C2, H2 times 2 is 4, plus 2 is 6, so we should have 6 hydrogens here. So let's count 1, 2, 3, 4, 5, 6. It does match, general formula is correct. Okay, so its functional group that you would notice that it's an alkane is having only single bonded carbon to hydrogen bonds. So there's a single bond between them, and having a single carbon to carbon bond. So the line, obviously, or this little arm drawn there, indicates one bond. Okay, what type of structure is it drawn in? It's not drawn in Lewis, but it's rather drawn in Cooper structure. Okay, we draw organic compounds structurally in Cooper structure and not in Lewis. Okay, just to define a couple of things quickly. What is a homologous series? Well, first of all, a homologous series is a group of compounds that contain the same functional group. So all alkanes have this functional group, no matter how many carbons or hydrogens they are, right? Because that's how you would see it or know it as if you look at it. It's the same functional group, all right? And that's why it can be described by the same general formula, CnH2n plus 2 for alkanes, right? So that's the first one, right? Very good table for this, for remembering the different homologous series. Having a look at alkenes, it's the next one, okay? This one has a similar general formula, CnH2n, meaning that there is 2 less hydrogens in an alkene as they would be in an alkane, right? Because we can see the plus 2 is taken away. Okay, so if we have 2 carbons here, which we would have here, suffix is "ene", so this wouldn't be ethane, but rather ethene. All right, ethene. And we see in ethene we have 2 carbons and 4 hydrogens. So let's say Cn, so C, place N with 2, C2, and then 2H2 times 2. 2 times 2 is 4, so we should have 4 hydrogens. So we should end up with C2H4. If we count in our example of alkenes, we'll find that we have 2 carbons and 4 hydrogens. Functional group is always denoted by the double bond oxygen. Sorry, the double bond carbon, not oxygen, sorry. Double bond carbon. Whenever we see, if we are given structural formula, if we are given the example, and we are asked to describe which homologous series it belongs to give that answer, because we can note the double bond carbon, we know it belongs to the homologous series of the alkenes. Almost sounds like different tribes. Almost. The third one being alkynes. All right, this one general formula is also slightly different from alkanes, is that it is CnH2n minus 2. Okay, and that is because it is denoted by a triple bond carbon. All right, as we see in the functional group. So whenever we look and we see a triple bond carbon, we know immediately that is alkynes, suffix "-ine", Y-N-E. Okay, so if we look at the example there, all right, we have 2 carbons, so let's check the general formula. Cn, replace N with 2 because N will be in the number of carbons. So 2, H2N, so 2 times 2 is 4, minus 2 is 2. So we end up with C2H2. So it's another 2 less hydrogens in an alkyne as in an alkane. So there's 4 hydrogens less actually. All right, as we go from alkanes to alkynes. Okay. And an example there, which we see over here. Okay, we had to name this substance. I have space to write it, so I'm going to go ahead and write it. It'll be ethine. That's what the name of this substance would be, or this, not substance, but organic compound would be ethine. Okay, the eth is the prefix, that stays the same because it's got 2 carbons, and then boom, add the suffix. Suffix being the ending letters of the word. Okay, alkynes. Not as widely tested, I've not seen a lot of this. Yeah, or an alkyne, I've not seen a lot. I have seen it, but it's not as widely tested, to be honest. More of the other organic compound homologous series that we're going to get to now is tested. Probably because there's more that we can do with it. more that we can ask. Haloalkanes or alkyl halides. Okay, what this is, it's alkanes. It's the same. It's an extension of alkanes. The only difference is that there's a halogen attached to it. All right. So haloalkanes is its common name. Other name is alkyl halides. Okay. So the reason why we show both names there is that what if they don't use haloalkanes in the exam, but they use the term alkyl halides? We know what we're talking about. We know what we're dealing with. This general formula is so similar to the alkanes general formula, CnH2n, but now it's plus 1 because we've taken one hydrogen away and we've added X. X is a variable placeholder for any one of the halogens, such as fluorine, chlorine, iodine, and bromine, which we see in the table there. Okay, so its functional group would be that of a normal alkane. All right, but how we'd notice that is because there's still single bond carbon to hydrogen, and there'll still be a single carbon to carbon bond. But how do we notice that is if we look for X. All right, X would be the halogen atom that is bonded to a carbon atom. So the halogen is bonded to the carbon in place of one hydrogen. All right. So we have another example there, which is basically the same as an alkane. We just swapped out hydrogen and we put in a halogen. We put in bromine. All right. And this, how we would write this, we'd write the halogen first before the organic compound name. So we'd write it as bromo. And because it's an alkane, the same thing, bromoethane. Okay, so it's got no suffix, as is the same as above, so it's bromoethane. That's how we'd write it, okay? And that is the first part of some of the homology series and their corresponding functional groups. There is another, we just count quickly, 1, 2, 3, 4, 5, and we managed to fit in 4 here. Alright, so don't worry about it. We're going to keep going on these, and then we'll unpack them closer, more closely and more specifically as we go along. Alright, so I'm going to get on drawing the second part in just a moment. Continue with the table just to go through it again. The next homology series is alcohols. Okay, now alcohols do exist in the medical industry. Of course, this is the type of alcohols we are talking about. Okay, these alcohols are, of course, very, very strong. I think if you had to drink pure ethanol, which is this organic compound structurally drawn right here, we'll get to the part where we draw or name things a bit more, okay, as we go along. But ethanol there, I'll just maybe write the example here. Ethanol, just this compound here. If you drink pure ethanol, you'll probably die. Okay? Because it's very, very strong alcohol. Okay? It's almost like it's alcohol in its purest form. Functional group would be denoted by the OH. Alright? The OH hydroxyl group. Alright, bonded to a carbon atom. Okay, that's how you would recognize an alcohol. Okay, its general formula, CN2N plus 1 OH. Okay, obviously I explained how the general formulas work, so I'm sure we all are familiar with that. Then the next homologous series group is aldehydes. Okay, unfortunately its prefix is at the beginning. Alright, its prefix, its suffix is at the beginning, so its suffix is the group's or the series prefix. General formula CnH2nO, and the way that we recognize it is by the double bond oxygen bonded to a carbon that has a hydrogen. Right, so there'll always be a double bond oxygen with a single bond hydrogen, and that's how you'd recognize the functional group of an aldehyde. Okay, so that would what's be called a carbonyl group, right, with a hydrogen atom that's bonded onto the same carbon atom as the double bond oxygen, as we can see in the drawing. An example of this compound over here would be, the name would be ethanol. Okay, ethanol. Okay, and these are tested and are asked in exams. Aldehydes, they are. The next one is ketones. Now, ketones, all right, are similar to aldehydes in terms of they have the same general formula, but structural formula, they are different. Okay, and the way we recognize it is, and I'll maybe just divert to the purple color again, is by looking for the double bond oxygen somewhere in the middle of the group. All right, in other words, there are no hydrogens bonded onto this carbon atom. All right, in the middle, carbon would have 2 arms. All right, we place 4 hydrogens, but now they take both of those arms and they bond it onto an oxygen. Okay, so that's how we recognize a double bond oxygen carbon atom in between 2 other carbon atoms which have hydrogens bonded onto them. Okay, notice that I have left out the hydrogens just to save time. Okay, but these place empty spaces here with the of the empty arms. At the end of the empty arms would be for hydrogens. Okay, I mean, we're just drawing them now for academic purposes, not answering an exam question. Okay, so don't get too confused. You can see that it's slightly different. You see the double bond oxygen in the middle here, and its suffix is -one. So in this case, we have 3 carbons and no longer 2. So it's not ethone, but propanone. Okay, propanone, that's what it's called. Okay, so if this was an alkane, it would be propane, but now we have a double bond oxygen in the middle there, propanone. And then of course we have the other homologous series, carboxylic acid. Okay, also very similar general formula to aldehydes and ketones, except it has now got 2 oxygens instead of 1. 2 oxygen atoms. So it's CnH2nO2. And its functional group has, like aldehydes and ketones, a double bond oxygen. But, let me change the color, sorry. Double bond oxygen right here. But bonded onto that same carbon atom is an OH hydroxyl group. Okay, so what would this example be? All right, as we can see here, we have ether because its suffix is OIC, which is oic acid. So we have ethanoic acid. Ethanoic acid. Okay, see the double bond oxygen bonded to the carbon atom, and on that same carbon atom where that is bonded to double bond oxygen, there is an OH hydroxyl group. Okay, so it's a carbonyl group, so it's carbonyl plus hydroxyl, and we call this little group here, I'll write the name for it over here in white, it's called carboxyl. It's called a carboxyl group because it has a carbonyl group and hydroxyl group onto it. So this is a hydroxyl, okay? OH is hydroxyl group. Carbonyl group is anything that's bonded to a carbon, so double bond oxygen or anything like that. Carbonyl plus hydroxyl, carboxyl group. The last group or in the homology series is called esters. Okay, so it's just one liner after one more row after the table, so I'm just going to not going to spend time drawing that right now. So esters is the name. Okay, now it has a general formula, GF general formula of CnH2nO2. Again, very similar general formula to carboxylic acid. All right, now esters and carboxylic acids plays a major role in the formation of an ester, which we will get to further along the line. Okay, it plays a major role in forming one. Okay, so how to recognize it? By looking at its functional group. All right, it's looking at its functional group, which I'll draw in white. Is you'll have a carbon with 3 hydrogens bonded to it. In the middle, you'll have your carbon with your double bond oxygen bonded to a single oxygen, and that is turned bonded to another carbon or carbonyl group. Okay, but its functional group is this part over here. If you see this in purple, which is like an L, all right, you know it's an ester. Okay, it's a carbonyl group with a single bond oxygen bonded onto the same carbon atom, which is this part here, as the double bond oxygen. Okay, that's its functional group. Okay, if we have a look at an example, which we'll do up top here. Okay, so let's say we have, and I have enough space to draw the hydrogens in, so I will now. Okay, C, double bond oxygen, single bond oxygen, there's my ester, bonded on to another CH3 rather. Okay, what will we name this compound as? All right, we have one carbon or carbonyl group with 3 hydrogens, so that's methyl. All right, and then we have another 2 of them over here, so methyl ethanoate. Okay, ethanoate being, you know, ethane has 2 carbons in them, methane has 1, so methyl ethanoate. And here's your methyl, and there's your ethanol, and there's your ethanol. Okay, so how is the ester formed? Obviously, let me just write down its suffix. Its suffix, of course, is this part over here, 08. 08, almost like a number. Okay, 08. Okay, obviously an ester is obviously formed by the joining of a carboxylic acid. It is formed, and this we'll only do later, but it's worth mentioning now, plus an alcohol. Okay, if you join these 2 together, you'll get ester. Okay, that's how it works. Okay, so we obviously had rather methanol, and then we had ethanoic acid, so that's where you get the ethanoate from, of course. Okay, so I think what's nice right now is that perhaps we can just have a look at a sorry, we could just have a look at an exercise where we can maybe just practice naming and recognizing the homologous series. I think they could be good for us, and obviously I'll go through it with you. So, and basic exercises, of course, basic questions, not going too in depth. The more in-depth questions, I'll obviously go into greater detail. Right, so no need to stress. Cool. So we have a little worksheet here, guys. Okay, and it's very similarly set up to an exam or test. There are multiple choice questions that exist for the section in paper 2 at the end of the year. Okay, it's just set up differently, and I will take time to take you through an exam question on this section as well. Okay, I'll take that time, so don't stress too much about it. Okay, so the first one, which one of the following compounds belongs to the same homology series, okay, as C3H8? Okay, so what's important is now they want to know which of the compounds belong to the same homology series as C3H8. Well, now we got to obviously test, okay? We have to obviously test. We have C3H8. All right. So now we know the first general formula for an alkane is CnH2n plus 2. So let's check. Well, Cn, let's say 3 H2 times 3 plus 2. So we have C3H3 times 2 is 6 plus 2 is 8. So we know this is an alkane. Alright, this is an alkane. Alright, more specifically, if you want to name it, we know that 1 carbon is methane, 2 would be ethane, 3 would be propane. So this would be propane. Okay, so we know it's an alkane. So now we go and we check each of these over here. Okay, we know it can't be A, because if we take for A, we say that it's C2H2, N is 2 plus 2. We know we're going to end up with more than that, so it's not A. Okay, A is too little. Alright, let's have a look here at B. Well, it can't be B because C3H8, here we have C3H6, so this looks like it's a alkene, okay, because we've taken 2 away, so this can't be. It looks like it can't be C either, because there we look like we have C3H4, so it's not increasing. But D looks like it might work. Let's try D. Alright, so D, if we say, well, C4, H2, 4 plus 2, let's check. So C4 stays the same. H4 times 2 is 8, plus 2 is 10. Oh, well, that definitely works. So therefore, our answer for the first one should be option D, and they did ask for which one, so it can only be one. Which one of the following compounds belongs to the same homologous series as C3H8? What did we do? We found out the homologous series, which was an alkane. Therefore, we found the other alkane, which is C4H10, alright, which is butane, and it's also an alkane, so it belongs to the same homologous series. We're happy. Do we see how we had a look at this one, how we deciphered it? So the main way that we deciphered it was just checking the general formula, find out which was the homologous series that C3H8 belonged to, and then sifting through all of the options. Alright, question 2. Which of the following is the fourth member of the alkenes? Alright, which of the following is the fourth member of the alkenes? Alright, so we're going to try and find out which of these belong to alkenes. Alright, so that's that homology series. Okay, you need to find out using the general formula for alkenes which one it is. Okay, so I'm going to give you about 2 minutes for this one, so it's only 2 marks. Okay, and then we'll come back and mark it. And that's all we have time for in this week's tutorial. Stay tuned for the next extension of organic chemistry as we dive a little bit deeper into this awesome topic.